Sorry for being late. I forgot my HDMI cable and microphone. So today I want to show you some more generative models. Okay. So first of all, I want to show some slides about the theoretical definition and concept about a GAN. And now I think most of you have the experience of using GAN or knowing what a GAN is. Okay, it means it is a generative adversarial network. So there is a generator and a discriminator. They will compete with each other, so that if we can train both of them very well, then the discriminator can tell the fake and the true images, and the generator can generate the realistic images. All right. But however, the beginning of a GAN is some random number. We call them latent code. Okay. We use the latent code through the generator to generate the images we want. So by definition, we say if there are some real-world images, and we call them xi here, and they have certain distribution. For example, a group of images of dog, or a group of images of house, of cat, of faces, they have certain distribution of their own. And now, if we have some random noise or random code, we want to sample those random variables, and through the generator, we can simulate results of the real-world images. Okay. So here, we call our random variable latent variable, and it has its own prior. And when we sample, usually we assume the random variable is a Gaussian distribution, but this is not absolutely right. You can define any kind of distribution, but Gaussian is the easiest one. Then we pass the latent variable to our generator to generate an image X. Okay. So what we want is our distribution latent will be the same as our image distribution. Okay. So this like we have the latent variable, and through a generator, then we get an image. So what we want to do is we want to train our generator so that it can generate very good images, or images we want. So what do we mean images we want? It means the generated images follow or have the same distribution as the real-world images. So this is a real-world image, and this is a generated image. We want there is a discriminator network which can tell the input image is a real image or a generated image. If it is a real image, then the discriminator will tell us, okay, it is real. If it is a generated image, the discriminator should tell us it is a fake image. Okay? So we need to train not only the generator, but also the discriminator, so that we hope the generated images will converge to the real-world images. Okay? So to train, again, we have the mini-max optimization equation. Here is the generator, and it will be discriminator check whether it is real or fake. If it is real, then the output of this term should be 1. And if it is fake, this will be 0. But that is the ideal case. Usually, because you have some usually our discriminator only can tell us the probability of the image. It means it will not absolutely 1 or 0. It is the value between 0 and 1. How likely the image is real or fake. So that the value in this parenthesis will be a value between 0 and 1. With the log function, it will be positive. It will be a negative value. And here, x is the real image generated by x. The x here is the real image. So it will be checked by the discriminator. And if it is a real image, then the discriminator will say, okay, the likelihood of the probability of the image is true is very high. So the likelihood here is approach to 1, and the log value will be close to 0, but slightly negative. So here, we want the result of the discriminator is 1 for real data, and we want the result of this term will be 0 for fake data. So, but our generator wants to generate the images like real data. Okay. So the next question is, how do we train the setting? There are 2 networks. Okay. And this is a mini-max term. It is not like the case when we train the classifier. There is an overall loss. We try to reduce the loss as much as possible. So for GANs, if we use a V equation to express this term, then what we want to do is there will reserve a lot of iterations. And for each iteration, we will update we will optimize the discriminator and the generator, each of them, step by step. So this is the difference between the homework 3, when you homework 2 or 3, when you train a network, there is only one loss function. Okay, so when we train the GAN networks, in the beginning, the discriminator is very well, and it's very good, but the generator is very weak, because when we have a lot of initial parameters, usually the generated images, the quality is very low, so that the discriminator can easily tell this is a fake image. Therefore, the loss for the generator, it changes slightly. So how to solve the problem? Okay, usually we will use another term, negative log discriminator, generator, and the latent function. When we use this equation, the gradient for the equation is much larger than the original term. So we will train it in the beginning, maybe in some training step, then we will switch to another loss function. So when we jointly train the discriminator and the generator, and when they reach or convert to optimum status, it means the generated images, its distribution will be the same as the real-world distribution. Okay. However, how to prove it? Okay, the mathematical proof for this equation is very, very, very long, so I skip it here. And okay, then I will show you some very famous methods for generative models. Okay, in the beginning, in 2015, the DC GAN was published, and then a few months ago, the perception loss style transfer method was published, and then there was a cycle GAN, and there are two important metrics. They are not generative. They are metrics to evaluate the quality of generated images, and their names are FID and LPIPS. Okay. At the same time, there are some very famous GAN. They were also developed and make it published. So the first one is Star GAN version 1, and almost at the same time, the Style GAN 0. At that time, Star GAN, there is no Star GAN. There is only progressive GAN. But why I say it is Style GAN 0, because for the 1, 2, 3, 4 types of GANs, they are developed by the same authors from the same company. So after introducing them, I hope you can understand how they prove the GAN architectures step by step. Okay, so let's talk about the DC GAN. Okay, so the DC GAN is important because, I should say, this is DC GAN, and this is another paper. The paper is named Unsupervised Representation Learning with Convolutional Generative Adversary Authority, Gung. This is this one. It is learning deconvolution network for semantic segmentation. So this CNN network is proposed to deal with the segmentation problem. Okay, but the interesting thing is, it is a network. In the beginning, the resolution is very high, and then in the middle, the resolution is very, very small, just 1 pixel, and then it goes up. So this for input image and an output expected segmentation result, it can learn the weight from an input image to an output segmentation map. Okay? So several months ago, the author of the DC GAN, it is the Radford. Okay, he found that he can just use the second half part, so that when he has a random noise input, he can use the second half part to train a generative. Okay, so what's the innovation here? Innovation here is, before this DC GAN was proposed by Goodfellow at first, it can only generate small images like CFA10. CFA10, the image size is only 32 by 32 pixels. But there are some deconvolution layers. Deconvolution layers means upsampling layers. So because of the upsampling layers used here, Radford used the same deconvolution layer in his GAN architecture, so that he can generate high resolution images. The high is how high? From the images, you can see this is 64 by 64. And if it extends more layers using more deconvolution or upsampling layers, theoretically, it can generate even larger and larger images. But however, there is a problem. How stable will be the CNN network? Okay, but at least in his paper, he shows this is a feasible way. Okay? So, and these are the results generated by his method. Okay? This is the LO-SUM data set. LO-SUM means large-scale scene understanding, and there are several subsets. One of them is bedroom. So you can see there are a lot of bedroom images in this slide. Okay, then a few months ago, there a few months ago, Justin Johnson is now he's the professor at the University of Michigan, and I use a lot of his slides, right? Okay. When he was still a PhD student at Stanford, he published this paper. Okay. It is a perception loss for real-time style transfer and supersolution. So it is not a GAN. It is just a method for style transfer or for supersolution. Okay. But since in this course we are not going to talk about the GAN, we are talking about any generative model. So I show this method here. Okay. The idea is now let's go back to VGG. Let's go to 2016. At that time, the state-of-the-art classification method is GoogleNet or VGG. Okay, and so he got the idea. Since we have very good classification CNN network, can we use the features there to do image style transfer? Okay. So he developed a method like this. Okay. So given a style image, okay, and a content image, he used a pre-trained VGG network on the ImageNet data set. Okay, so there are a lot of layers in the VGG set. So for each layer, when the style target image will generate several feature maps, and the content target will also have several feature maps. So he wants to solve an optimization problem for the Y. So the Y image should have some similar feature maps for the style target image at certain layers, and have some feature maps similar to the content target images. Okay, so he defines two types of loss. The first is style construction loss, and another is feature construction loss. Right? Okay. So let's go back to the development of discriminative functions. Okay, this is the before 2021. Okay, there are some classification methods developed use the handcrafted features. And 2021, AlexNet was proposed. And then 1 year later, the ZF GAN is the slightly, extension of AlexNet. And they find a better set of hyperparameters, so that further improve the performance. Okay, then this is a VGG. VGG is a simple structure, but it's a more depth architecture. So you see, in AlexNet and ZFNet, there are only 8 layers. But in VGG, there are 2 versions, VGG 16 and VGG 19. This means the number of their layers. And at the same time, there was another approach developed by Google. There's a GoogleNet. Okay, but there are still more layers. And then ResNet was published. Okay, ResNet has at the most 152 layers. the more layers, the better performance. But this is not so easy, because if you have more layers, you need to have a good designed architecture so that the gradient won't explode or not vanish in the deeper layers. Okay, so let's take a look of the VGG architecture. Okay, so this is AlexNet. You can see they have different filter kernels. This is 5 by 5, and this is 3 by 3, and 3 by 3. And in the beginning, there is 11 by 11 filter kernel. But for VGG 16 and 19, all convolution layers, their convolution size is only 3 by 3. Okay. So their design rule is they won't use the 3 by 3 layers, but they want to try if they stack up those 3 by 3 convolution layers more deeper and deeper, how about its performance? Because even though the convolution kernel, filter kernel is only 3 by 3, because if they use 2 layers together, the actual perception view field will be 5 by 5. And if they stack one more layers, the perception field of view will be 7 by 7. Okay, so if they have very, very deep structures, they can see the whole image. Okay. So because of the regular structure, they named those layers. So this is stage 1, okay, stage 2, and stage 3, stage 4. It's very similar. 2 convolution layer and a pooling layer, 2 convolution layer and 1 pooling layer. Here they have 3 convolution layer, 1 pooling layer, 3 convolution layer. Okay, and in the VGG19, the only difference is there is 1 more layer here. Okay, so okay, they have the tool as a VGG network. And then let's go back to their idea. Okay, so the next question is, which layer should they use to let the style target image be similar to the output image, and which layer should be used for the structure or I just said they want to get colors, textures from the style target, but they want to preserve the shape from the content target. So the result was like that. You can still see the shape of the tennis player, but you see a lot of patterns or textures from the style target. Okay. So how to do it? They have to observe which layer will generate the results they want. So it means they have to go through all layers using their eyes to see, from this layer, okay, I see it preserves the features I want. So let's take a look. If this is the input image, okay, then the ReLU 1, 2. ReLU 1, 2 means this is stage 1, the second layer. So this is ReLU 1, 2. And this is ReLU 2, 2. Okay, so this is a ReLU 2, 2. And this is ReLU 3, 3 and ReLU 4, 4. ReLU 3, 3 and ReLU 4, 4 is here. Okay? Oh, sorry, ReLU 4, 3, 4, 3 is here. So for this image, when they use VGG to process the input image, they observe this. So what does it mean? For the 4 layers, ReLU 1, 2, ReLU 2, 2, ReLU 3, 3, and ReLU 4, 3, those layers learn what? Learn colors from the input image, or the textures from the input image. Do they learn the structure from the input image? No. So what is mean structure? So this is another example. There are two elephants, right? And if when they observe the ReLU 22 and the ReLU 33, ReLU 43, so they see the shape or the structure of the two elephants gradually disappear. But at least on the layer of ReLU 22 and ReLU 33, they can still see some structure there. So, so it means they manually pick up some layers for the style preserving and the structure preserving task. Therefore, they define some loss. Okay. So this is the feature reconstruction loss. This is the sorry. Here, this is the feature reconstruction. They choose ReLU 33 to met the feature extraction loss. And they also create another style construction loss. Okay, so the structure construction loss is slightly complex because they need to compute the GAN matrix at first. So this is a GAN matrix. Now, and they use two GAN matrices. They will generate the style construction loss. Then, now they have the feature construction loss and the style construction loss. They put those loss in this optimization term. So this is a feature construction loss, and this is hyperparameter lambda c, and the style construction loss, and another hyperparameter lambda s, and this is a regularization term. So this regularization is named total variation. It means for two adjacent pixels, they hope their intensity won't change too large. Why it makes sense? Because for most natural images, there are a lot of smooth area. The gradient between two pixels are relatively small, and there are only a few very sharp edges, so their gradient is very large. Therefore, the overall total variation term should not be very, very large. So you can imagine, for what kind of image, the total variation term will be very large. For an image, there are a lot of Gaussian noise. Almost for if every pixel is a random value or random number, then the difference between one pixel to its surrounding pixels will be very large. So therefore, the total variation value will be very large. So they use the optimization term, to find an optimal output image. That is Y, and we can see their results. So this is a style. They want to have textures or colors from this, and this is the content. Combine the style and the content. This is their generated image, and this is another one. The style images are the same, but the content image is different. This is another example. They use a Simpson cartoon image as the style, and they use a cat as the content, and a man in the content, so they generate the result. Before this method, there are some existing style transferring method already. So this is the example 10. 10 is another paper called a neutral algorithm of heuristic style. It uses convolutional network to transfer image. So compare with the two generated images, the structure are similar, but the color are not totally the same. But both of them are like the style input. So if so, what is the improvement of their method? The execution time. So For gate method, it requires many iterations. Okay. So to generate a 256 square pixel images, it may use, if it run 100 iterations, it takes 3 seconds to generate the image. Okay, 3 seconds or 3 minutes. 3 seconds, right? And Justin Johnson's method only needs 0.01 seconds, so it's much faster. Okay, so the speed up is 200 times. Yet if want to generate higher quality images, it needs more time to do it, so the speed up will be even higher. But however, for users, they don't feel there are a lot of difference in terms of the image quality, but the method, it can run very, very fast. So this is an improvement. Okay, their method can only be applied for another task called single image super resolution. Okay. This is, they have a lot of training images from the NS-COCO dataset. Okay, so their content target will be the high resolution image, and their input image will be the low resolution generated by themselves. So when they use a pair of images, this is the YC, and the content image, when they put the content image into the VGG dataset, there will be a lot of layers. Okay, and then they create an image transform network. What is that? In fact, it is the modified DC-GAN. So that's the connection between this paper and the DC-GAN, because they use, DC-GAN was published a year or several months before. They found, oh, it's interesting. So they use the DC-GAN and then slightly more, because let's take a look at the DC-GAN. Okay, the DC-GAN, what's the input of DC-GAN? Random noise. So it is not an image input. They need to modify the DC-GAN so that they can feed the generator, or it's not just feed the convolutional network a low resolution input as is. Then again, okay, there is a modified DC-GAN which can generate a high resolution image. So you can see that's the contribution of this year, because it can generate a high resolution image as high as you want. Okay, but for their case, they only test scaling factor 4. It means the width and height for the low resolution image is only 1/4 of the height of width of the high resolution image. So for DC-GAN, it just needs 2 upsampling or 2 deconvolution layers. It can generate 4 times larger images. Okay, so they use the same idea, but here they don't need to use the feature reconstruction loss anymore, because why? They want to preserve the same content and the same style. So they don't need like this. There are several laws to preserve the style. Okay, so they use 10,000 images from the NS-COCO dataset to train the DC-GAN, okay, or the modified DC-GAN, and they simply just use the ReLU 2 layers feature maps to compute the reconstruction feature loss. Okay, so after training the 10,000 images, okay, they can just forget all of this part, and they get a upsampling network, this one. And this is their result. So the baby face is the benchmark image for single image super resolution in 2016. So this is the ground truth. You can see the eyelash very clearly. But when you downsample it and upsample it again, the details usually disappear. Therefore, when you use the bicubic interpolation method, you do not, you only see something very blurred here, okay? And this is their result, and this is another setting of their result. They will calculate the loss pixel by pixel, so it looks like they want, and the SRCN is the state-of-the-art method. It was in that year. It was proposed by Kai-Ming He. And who is Kai-Ming He? He is the developer of ResNet. Okay, so before ResNet, he proposed another convolution for another CNN network for super resolution. Okay, and so here, the loss is the VGG feature loss. It means they want to show when they use the VGG feature map as the loss function, they can generate very high quality, high resolution images. Okay, but however, here let's see two metrics used in that year. It is PSNR and SIN. PSNR just the point signal to noise ratio. Okay, peak signal to, and the SSI means structure similarity. The two metrics are, okay, I should say, in 2016, they are no better or more convincing metrics. So the researchers in that year, they have no other way. Either they use this, other they they do human subjective study. Okay, so let's see. The PSNR is the higher the better, and the same as the SSIN. But when you just see numbers generated by the two metrics, theirs are not the best one. They are only 29, but for the three other methods, the number are all greater than 30. And their PSNR is also less than 0.8, and all others are greater than 0.8. So they want to show the readers it is a problem of the PSNR and SIN metrics, not their image results, because PSNR and SIN only measure the similarity, but for our human perception, similarity may not be the most important one. Our eyes prefer to see some very clear, sharp edges or details, but those sharp details may not be the same as the original one. Okay, so this is a set of 5. Set of 5 means there is a group of 5 images, and the 5 images are also those benchmarks for single image super resolutions. Okay, so we can see the same result. They do not generate the best PSNR SSIN metrics index. Okay, so this is another test set. This image belongs to another set called set 14. Okay, there are 14 images. And the BSD 100 means Berkeley segmentation data set. There are 100 images. The resolution is around 300 by 200. Okay, it was originally designed for segmentation task. Okay, but it was popular for super resolution in that year. Okay, so the same. So compare with this, we still can see their method generated very sharp edges, and the sharp edges are preferred by many users and also preferred by the BGG network, so that they can use BGG networks to generate sharp images. Okay, and then let's go back to GAN. Okay. This cycle GAN is, important method in the development history of GAN. So let's see what they want to solve. Okay. Let's see what they can do at first. So this is the image. Okay, it's like a painting from Monet, and this is the real photo. They can transfer the real photo into the style of Monet and transfer it back. Okay. So, and there are two images. One is a zebra and another is a horse. Their method can transfer the horse image into a zebra image and transfer it back. So then, like this one, this is horse to zebra, and this is zebra to horse. So this is summer to winter and winter to summer. Okay. This is okay. So they also can transfer an image to Monet, Van Gogh, Cezanne, and Chih-Yuan. Okay. So let's see how do it. Before the cycle GAN, many style transfer methods need paired input image as training data. So what is paired image? So this is a scratch and this is a real image. They share the same shape. And this is another, okay, so they need many paired image to train their GAN. But in cycle GAN, they say it's troublesome. So let's develop a method. We can just need two collections of images, one for a domain, for example, real images, and another for another domain, so for this painting. Okay. Sorry, that's mine. I forgot to turn it off. Where is, okay, this is off. Then, okay, this is the innovation. They created two generators. This is G and this is F, and the two discriminators dx and dy. So see, this is not totally the same as the existing GAN definition because there was only one generator and one discriminator. At the beginning from cycle GAN, they can use multiple generators and then multiple discriminators. So what they want is their generator. Alright, okay, let's take a break. Until now, do you have any question want to ask? If no, let's keep going on. Alright, so we say their innovations, they train a pair of generator, G and F, and a pair of two individual discriminator dx and dy for two different domains. Okay, so now what they want to reduce is if they have an image in the X domain, say a painting, okay, and they transfer the painting image into a real photo images, and use the F generator to transit back. What do they want? They want the new images in the X space should be similar to its original image. The same, the real photo transfer into a painting and transfer it back, it should be very similar. So that is a very simple, very intuitive idea. Okay, and just developed two generators and two discriminators to do it. So they can generate very interesting result. So this is input image, and transfer it to, so this is a real image, transfer it into a painting and transfer it back. So this is a horse, transfer it to zebra and translate it to back. So this is winter, transfer to summer and winter back. This is map. This is the, what it is? Oh no, this is a satellite photo, and this is a map and translate it back. So they want the reconstructed image will be very similar to the input image, so that they can transfer not one way but another way. It's like a circle. So this reason the name is called circle GAN. Okay, so let's see what's the connection between circle GAN and the Justin-Johnson's method. It means they just use Justin-Johnson's network to Justin-Johnson used what? Used the modified DC GAN. They use Justin-Johnson's architecture as their GNS. Okay. So this is their comparison. Given the input real natural image, and okay, there are three different. I should say, in 2016, Gates method is the state of art. It is the transfer method. We saw it a few slides before. No, not this one. Okay, Gates right here. Okay. No. So this is the Gates method. Again, they compare. I mean, the cycle GAN also compare their method with Gates method. And let's see their results. Okay. So Gates method requires a reference style input image. So this is a reference input, and this is the image want to transfer. So the style from this image and the structure from this. So this is the result generated by Gates method. If they use another style image, they will generate another output result. Okay, and this is a collection, means they have several images in a collection and use the collections to generate output. So it's partial like this and partial like another one. But for cycle GAN, okay, so visually, which is better? Well, it's hard to say. Okay. But however, they want to show us their method can generate the result as good as the Gates method. But however, the advantage, they can transfer it back and very stable. Cool. So how to see the stable? Let's see another slide. Okay. So for this apple image, if they use orange as the input reference, this is the result. If they use mango, this is general result. And if they use both mango, orange, and some other fruits, maybe grape or something, okay, this is the result. Well, so this is the result generated by cycle GAN. And this is horse to zebra. In this case, there are two types of zebra. So this style, actually this input image and this image, both of them are zebra. But however, their styles are different. Therefore, they generate a different style. And when you use the collection, then there are some problems. I should say there are some artifacts. For example, in the sky, it generates some zebra stripes here, and they only generate the partial zebra patterns on the horse. But the authors of cycle GANs, they want to show, okay, their method can generate a better result, more stable, more consistent. But usually, there are some failure cases. So let's see some interest. The merit of this paper is they show many failure cases. Okay. They show, okay, for this input, as an apple, although they have two sets of unpaired images. For example, this is apple and this is orange to train the cycle GAN. But it doesn't guarantee every image can be well transferred. This is example. But the generated image doesn't look like an orange. It's like a yellow apple. Okay. And for this zebra doesn't become a horse. Okay, it is still a zebra. And okay, for this example, this is protein, I think protein. Okay, and he is riding a horse, but their GAN doesn't tell this is a human. So it also transfer the image into something very unusual. Okay, so this is an interesting failure case. And when they have dog and cat cases, dog doesn't transfer to cat, and the cat doesn't transfer to dog. So that is the interesting thing of GAN. The idea is very simple, just to try to reduce the difference when the GAN is reconstructed. But however, it may not work for any type of image because images are very, very complex data. Okay, then, in 1 year later, there is a very famous GAN called GAN. It was published in CPR 18. And it was derived by the Never Cope. So do you know what is Never Cope? You may not know it, but do you use Line? Yeah, Line is the app on your cell phone. Okay. Never is the mother company of the Line company. So okay, so they have a top goal. You know cycle GAN. Let's go back to cycle GAN. The cycle GAN can transfer images between two domains. So it's like a cycle. But however, if we want to multiple domains, can cycle GAN do it? No, cannot. The one way is we train multiple cycle GAN. So we can transfer domain A to domain B to domain A, then domain A to domain C to domain A. So it is not very convenient. Okay, so they developed a new architecture called star GAN. Why it's called star means because you see there are some endpoints of a star. Usually there's 5 or 6 endpoints. Okay, so it means from the center, they can transfer the image to multiple domains. So it is called star GAN. So in this illustration figure, you can see this is input image. And then there are at least 4 domains. Blonde hair, so this is gender means male and female. Age is young and old. And palm skin is, okay, so this is palm, so it's brighter. And this is not palm, so it is darker or yellower. Okay, so for another domain, they use the red bound face data set. There are 8 different facial expressions, and angry, happy, and fearful are 3 of them. So they can transfer one input image to any or multiple domains. So let's see how they developed this GAN. First, I need to introduce the celeb A dataset. Okay. The full name of celeb A is celebrity face attribute. Let's tell a story. In the beginning, there are some researchers. They create the celeb face dataset. There is no attribute. It means just a collection, several thousand images. Okay, but almost no label. all of them come from celebrities. That's all. Okay. So they, as you said, in 2015, okay, Liu et al. They add attribute into the celeb face dataset. It becomes the celeb A. A means attributes. Then, how large is the dataset? There are 200,000 plus images that come from 10K identities. And they also add landmark locations and the binary attributes. So what kind of attributes? Whether they are smiling, whether their off is oval, and where they are wearing hats. So all of the 40 attributes are binary values, either true or false. Okay. And the resolution of the celeb A dataset varies a lot, from very small image to very large image. Okay. So let's see how GAN works. So again, so this part is very similar to GAN. There are they use a label. It is a one-hot vector. So it's so like this. For this case, the one-hot vector have 4 elements, just the blonde hair, gender, age, and the pumpkin. So, and when they want to convert one image to another domain, they just need to tune the one-hot vector. So, do you know what is one-hot vector? One-hot vector, this is a one-dimensional vector, and every element is either 0 or 1. Okay. So, for this case, if there are 4 domains, then the one-hot vector is a one-dimensional vector with 4 elements. Either is 0, 1. If the first element is 1, it means blonde hair domain. And if the second element is 1, it means the gender, the male or female domain. Okay, so and there will be only one element is 1. All other elements are 0. Okay, they introduce the domain label is a one-hot vector to control to condition the generator, so that it can generate images. And when they want to transfer it back, they just need to tune the one-hot vector back. Okay, so if this is in the beginning, this is a male image, and they set the gender as female, and they will create a female image. And they then set the one-hot vector as male and can transfer it back. That it should become a female image again. So the idea here is very, very similar to GAN. So this is the connection between GAN and GAN. Okay, then developed a discriminator, okay, to tell this is a true or fake images. And the discriminator also need to classify the domain, because for GAN there's only 2 domains. So they use 2 discriminators, right? But here GAN has multiple domains. So, but they only train a single discriminator. But the discriminator need to understand which the domain is from the given image. Okay, so this is the architecture. Conceptually, it's not difficult to understand. Okay? But how to implement it? They release their code on GitHub. If you are interested, you can take a look. Okay. So let's see their results. So the diet, okay, GAN is here, and this is their GAN. So for GAN, There are 1, 2, 3, 4, 5, 6, 7, 8. They need to train 8 cycle GANs. Each one can transfer input to a certain domain and back. But for star GAN, they just need to train a single generator. And the generator has 4 domains. So just 1, 2, or maybe 3, only 3. Because black hair and blonde hair are the binary choice. Okay? And the gender age. And this is hair plus gender, hair plus age. This is gender plus age, and this is all of them. Okay? So they can transfer the style into at least 3 domains and then the combination. Okay, in addition, so what are the attributes? Those age, gender, and the blonde hair are the attributes in the select A dataset. So they do not need to reinvent those attributes. They are existing properties, just take it and use it. And then this is the ray-fold phase dataset. Okay, there are several labels. Contemptuous, disgusted, fearful, happy, sad, surprised, angry. Okay, there's 1, 2, 3, 4, 5, 6, 7, and the 8th is neutral. So usually this is the neutral. Okay, they transfer the neutral to either of them and transfer it back. Okay. And as I say, until 2011, there is no very effective metrics to measure the quality of images generated by GANs. So they seek for human subjective studies. It means they generate a lot of images, and they ask Turk from Emerald Mechanical Turk, okay, to pay them which image do you prefer, okay, and then they collect those data back. It shows for gender, age, and hair colors, their method generate images with the highest, I should say, more favored by most Turkers. Again, okay, for the combination, they also achieve, they are the most favorable. Okay. So let's go back to this slide. Here, this is the time StarGAN version 1 was released. And okay, FID is an effective method to measure the image quality generated by GANs. But it was just uploaded to archive, and it hadn't been published by a major conference, so it is not widely known. As a result, StarGAN authors, I thought they didn't know the seed metric, so that they didn't use the seed metric. And after the publication, there is another metric called LPIPs. So then, when we talk about StarGAN v2, you will see StarGAN v2 use FID and LPIPs to measure their performance. Okay, then 2 years later, they published another method called StarGAN v2. Okay. So the architecture changes in several ways, but their goal is the same. They want to transfer styles from image to another image. So let's take a look. So this is the input image. They want to transfer gender, so from this male image to the female images, and there are several different domains. Again, this is the female image, and they want to transfer it to a male image. So this 3 images are generated by GAN v2. They also create another dataset called AFHQ, Animal Face High Quality Image. So this is the input image. It's a cat, and they want to transfer it to dog, and transfer it to tiger and jaguar. Okay, and given a lion, it can transfer the GAN can transfer it to cat, dog, tiger, or jaguar. So this is the style transfer. So let's see what is for the generated image and the input image. What do they share? You can see they share the orientation of the face. Okay, and they also share what? Okay, for example, they also share the shape of the mouth and I should say what? The location of those feature components. Okay, see, so I need to, they use celeb AHQ. So let's go back to the celeb A dataset. You can see the resolution of those images in celeb A changes a lot, from very small to very large. So you can also imagine the quality of those images also changes a lot. So even the dataset is very, very large, some of the images are almost useless. Therefore, there is a celeb AHQ dataset. Okay. However, the celeb AHQ dataset was not compiled by GAN v2. It was compiled by progressive GAN. Okay. So what is progressive GAN? Progressive GAN is the previous generation of style GAN. Okay. So the first author is Karras. He published 5 papers all about the style GAN. Okay. So you compare with the select A dataset, there are fewer images, but all of those images are the same resolution and high quality, and all of them are aligned at the 2 eyes. Okay. And the AFHQ dataset was compiled by the GAN v2 team. Okay. So there are 15K images, and the resolution is slightly smaller, and it was divided by 3 classes: dog, cat, and wildlife. Each of them has 5K images. So let's take a look of the GAN architecture. Okay. So what's the difference compared with GAN? First, there's no cycle architecture. They took it away. Okay. And there's no one-hot domain labels. Okay. They use a style code. It is a 64-dimensional vector instead. So why do they need? Okay, I will explain what's the benefit of this. Okay, because they use the style code, the code can be generated by a reference image, or just set it as a random variable, like the Latin code for the for the GAN proposed by Goodfellow. All right. So because there is no circle, so how do they calculate the difference between different domains? So they created the structure of a multi-height discriminator and a multi-height style encoder. Okay, all of them are multi-height. Okay, and then they add R1 regularization and add some diversity regularization. Okay, let's see their result. So this is the input image, okay, and this is a reference image. In StarGAN1, they need a label to specify, okay, I want to generate a gender or different genders or different hair colors or different skin colors. But in StarGAN V2, they just need a reference image. So they will use the structure of the source image, but the style from the reference image to generate a new image. Okay. So if you see the same column, you will see their orientation are the same. Like this one, all of the generated images share the same left, no, I should say, their orientation are slightly leftward, rightwarded or something. Okay, and because the reference image provides the style, so if you see the same row, you will see all of the generated images share the same gender as the style one, and the same hair color, skin color, and even the color of the lips. Okay, so I didn't finish this sentence. Okay, right, and see more results. Okay, so as a habit, they need to compare with the state-of-the-art method so that their reviewers will be easier to judge their contribution. So they compare the two methods, DIRT and NSGAN. So this is their generated image, and these are two images generated by the two methods. So let's take a look at the qualitative comparison. Not bad. Do you think so? Okay. And right, so there is a quantitative comparison. StarGAN V2 was published in 2019, 4 years ago. Okay, so there are FID and LPIP available. So they use FID and LPIP-S to evaluate their performance of the GAN. Let's see. For StarGAN 1, FID value is 19.8, and with the multi-head discriminator and some R1 regularization, latent co-injection, and each of the new designs slightly reduce the FID value. The lower the FID value, the better. I should not say the better. I should say, according to the assumption of the FID value, the lower should be better. But this is not always the case. And LPIP, okay, it is a measure it's a matrix to measure the difference between two patches. It's only for patches. And the StarGAN V2 extend it to measure the difference between generated images. So what does it mean? It means you know a GAN can generate a lot of images, right? And if all of them are the same, it will be not a good GAN. So a GAN should generate images belonging to the same group, but they look like different. So LPIP measure the differences between those images. So the better, the more variant, the larger the LPIP values. So from this table, they want to show their StarGAN V2 not only generate very realistic images, but also highly variant images. Okay. So compare with some existing methods, they show their performance is better than others. Okay, and they also ask emerald mechanical targets to do the same because they want to show more evidence to convince their readers and reviewers. So this is a human subjective study. Their images are also more preferable in terms of quality or style. So quality is similar like the FID. It means how similar to the ground truth images. And style means how various those generated images will be. Okay, so this is the network architecture for the GAN V2. So let's take a look for a generator. Okay, this is the input image. So the resolution is 250 square, and there are some convolutional and layers. Finally, it will become a 16 by 16 image. So in the beginning, it's slightly reduced, and then there are some upsampling there or deconvolution layers, and this is a adaptive instance normalization. We talked about instance normalization in our previous course, and the adaptive normalized instance means they will, in the instance normalization, we will learn two parameters, the scale parameter and the bias parameter. The adaptive instance normalization means we can change the value. The scalar vector and the bias vector are learnable. Therefore, that's the reason why they can transfer styles from one image to another image, because they can control the parameters in this adaptive instance normalization layers. Okay, so this is the style transfer. This is a style encoder architecture. Okay, given an image, they will go through several layers. All of them are pooling and convolution. Then it will generate a vector. I should say not a vector. The D means vector for one domain. The K means the number of domains. So it will generate output result as a D by K matrix. Okay. All right. Okay. So for style GAN V2, its code is also available. Okay. And there are very clear instructions to teach users how to train their network. So, but however, it takes 3 days on a single Tesla V100 GPU to train the overall network using the dataset. And our AI center have the same GPU, Tesla V100. So if you are, if you are interested, you can reproduce their results. Okay. And there's another interesting thing. In their paper, I cannot find the drawback or limitation. Just like a cycle GAN, we see a lot of failure cases, right? For style GAN V2, there must be. And I did it once. And I found there's problems. For example, there is a dog in the foreground, and there are some background. And the generated image, usually, sometimes it will make mistakes. It will transfer the background of the dog to the subject of the generated image. Okay, but the authors of style GAN V2 didn't mention it. So if you want to do research, okay, usually we will try to reproduce the result of some existing methods and see what we can improve. Okay. We know FID and LPIP metrics were used in GAN v2, but what's the definition of LPIP and FID? So the full name of FID is frame rate inception distance. Okay, it was proposed by a paper, GANs trained by 2 time scale after that. It was published in NIPS 17. So the idea is, let me explain the idea. Okay, it means inception ratio is a discriminative convolutional network, and let's then pre-train it on the ImageNet dataset. Okay, so it will have very good classification property. It means the feature before the final fully connected, it can well represent the image. It means it converts the images from the RGB color space domain to feature domain. Okay. Then it assumes if there are 2 groups of images, one is the real world images, and another is the generated images. If they are highly similar, then there are a lot of features in the feature space. The mean and the variance of the 2 groups of feature points should be similar. So, but however, we don't know the distribution of those feature points. So they assume they are Gaussian. So this is a very strong and straightforward assumption. But for most cases, it works. So this is an interesting part. Okay. But later we will show some cases it doesn't work. So they measure since if they assume they are Gaussian distribution, so they define the frame trace inception distance will be the distance of the 2 means and the scalators of the 2 distributions. And they show some examples. Okay, you know Gaussian noise in the very early beginning. So for a given image, and if we apply Gaussian noise at a different label, then we will generate a group of images, right? Because you know Gaussian values, so it will alter the pixel values in any channel. Okay? So for the low level, middle level, and the high level Gaussian noise, we will generate a lot of images, and we compute the FID value between this group and this group, and we will get a FID value. And this group and this group, we will get another FID value. So it looks very intuitive. If we have a very high level of distortion, then the FID value becomes larger. So this is a Gaussian distribution, and this is blurring, Gaussian blurring. So high level blurring, middle level, and low level. Okay, their FID value continuously increase. Good. So this is a corruption. It means just crop some regions out. Low level, middle level, high level. It also looks good. And this is the swirled image. So for different level, it also makes sense. So and this is paper and salt noise. Okay. For this type of distortion, the FID metric doesn't work very well. Okay, it's almost the same. Okay, so this is this is for a group of images, and this is from Celeb A. And if we replace some of the selected images with images from ImageNet, so you can see there are two types of different images. If we replace more images from the ImageNet datasets, then the FID value will continually increase. So it makes sense. And it means FID is a, very intuitive metric. Okay, and then the LIP metric is slightly complicated. Okay, so the full name of the LPIPS metric is Learned Perceptual Image Patch Similarity. Okay, it was proposed in CPR 18, and the group. Okay, the idea is because there are some existing discriminative network, BGG, AlexNet, EfficientNet, and ResNet, etc. Okay, all of them work well for discrimination. It means they all transfer the images from image space to the feature space, and then they can well distinguish those features. So, first of all, for this example, if this is a reference image, and they given two patches, they first ask human subjectives, which one is the image more like the reference image. So from this and this, human usually will choose this. But PSNR, SSIN, I mean those existing metric, they will say, okay, this patch 0 is more close to the reference image. So that's the problem. As why we say here, okay, that's why I say here. Justin Johnson, for his super resolution text, he has shown us PSIN and PSNR and SIN are not very useful to measure the perception difference. But in 2016, LPIPS is not available, so they cannot use LPIPS. So, okay. For this example, the same. This is a reference. They given two patch. They ask which one is more close to the reference match. Human usually will choose this, but the PSNR and SIN will choose this. So they want to develop a method to solve the problem. They want to develop a new matrix more close to human perception rather than PSNR and SSIN. So how do they do? First, they need to build up a data set. So they create a BAPPS data set. The full name is Berkeley Adobe Perceptual Patch Similarity. So there are two types of data. One is the two-way FC test, just like the one. Given a referencing patch and the two patches, they want to know for humans which one is the most similar. Okay. So another is just a noticeable difference. Given two patches, they ask the humans, do you see a difference between the two patches? You can answer yes or no. Okay. So they compile the dataset containing many patches. So the total number is around 119K patches. Okay, so this is a spec. Okay. Then there are many different distortion types. So this is a traditional distortion types. This is like Gaussian. No, this is blurring. This is very clear. And okay, so I will show. Okay, this is a list of list distortions. Because the research was did in 2018, just 5 years ago. So there are many distortions were created by convolutional networks. So in addition to traditional distortion, they also create a dataset for the convolutional-based distortion. So look like this one. There are a lot of strange patterns. Okay. However, they create a dataset containing a lot of distortion, and because they won't know what kind of distortion will happen in the future, so they collect as much as possible. Okay. So their method is somehow very simple. Okay, given a existing convolutional neural network like a BGG or AlexNet or SequenceNet, any kind of discriminative convolutional network. So given two patches, X and X0, and then the convolutional network was pre-trained on ImageNet. So this is they browse all of those parameters to generate feature maps. Okay, for the two patches, they will generate two sets of feature maps. Then they want to learn some. Then just compute the differences between those feature maps and learn some weight here, so that they will convert those difference of feature maps into a single value. Okay. So what's the meaning of a single value? It means if X is the reference image and X0 is one of the two pairs, the patch 1 or patch 0, here, either here, okay? And then patch 1 will generate a distance d1, and patch 2 will generate another distance d2. They can learn those parameters so that for this case, d1 will smaller than d2. So it will match humans' perception. Okay, then they show their results. There are different settings for VGG, for AlexNet, and for SequenceNet. And they found their methods are very useful. Compared with SISIN and PSNR, the performance are all better, no matter what kind of discriminative network they used. Alright, so, okay. As far as I know, for example, they add, for the GAN v2, they add the regularization for, okay, here. They add the diversity regularization, right? But so that they increase the LPIP values, okay? And they also say replace D with the style code. So this is another approach to increase the LPIP value. Therefore, if you, so as for your question, LPIP is a matrix. So how to use LPIPs to improve the diversity? I'm not totally sure. Maybe, maybe not. I haven't read any papers show how to do it. Okay. So from GAN v2, maybe I can check what are the diversity regulation they use. Okay, to increase the diversity of your GAN. But so far, I haven't seen any method use LPIP because it's just like a matrix. So I think it's possible you optimize your GAN with respect to that matrix. It is possible. But however, see, when we train a GAN or train a network, we need some backpropagation. But how to create a generated backpropagation from LPFS? I have no idea. So this is a very interesting question. So do you have other questions? If no, then let's go on. So because LPFP is much better than SI and PSNR, so after the paper was published, almost no one used PSNR as SI anymore. They use LPFP. And they released their code and the pre-trained data on GitHub. Because you see, LPFP relies on pre-trained network. So from their example, you need to specify which pre-trained network you would like to use, either VGG or LexNet or something else. And the default is VGG because its performance is better than Linux. All right, then we will discuss about 4 papers about style GAN. So let's take a look over. Okay, just see the chart. This is the time list 1, 2, 0, 1, 2, 3. Okay. And you can find their papers from archives or different conferences. So first, the progressive GAN. The idea is, they created the celeb AHQ for progressive GAN, just like this. And there are examples of celeb AHQ. And the idea is simple. To train a generator is very difficult. Okay, so how to do? They train it progressively. In the beginning, just train a 4x4 generator and the discriminator. Then in second step, train an 8x8. So they add 2 layers, one for generator and another for discriminator. And then they can progressively increase the layer of generator and discriminator. So this will create a large GAN. So when they add a new layers, they use some tricks and methods. For example, they create something like a ResNet. When they set alpha as 0, okay, it will become the original. So because alpha is here, when alpha is 0, it is identical to its 16 by 16 layer. And they increase the alpha linearly from 0 to 1. It means when the alpha is 1, the 32 by 32 layer works for the new GAN. Okay. And they will generate the network. So this is their final result. Beginning from 4x4 and then 8x8, 16x6. And finally, it generates the 1024 square. And for discriminator, the same. From 100, it's from 4x4, 8x8, 16x6, and finally 1024 square. Okay. So in fact, the progress GAN generated a very good result. But 1 year later, they proposed the style GAN V1. Let's take a look of the difference. So this, they call the traditional GAN, just the progressive GAN. You have a latent random variable, and then you will go through many layers in a generator and generate the image result. So in style GAN V1, they create this mapping network F. It means from a random variable, usually this is a Gaussian distribution, then through this mapping network, there are many layers. They will create another distribution in a latent space W. When the variable Z is a Gaussian distribution in the Z space, it is not a Gaussian distribution in the W space. And in the W space, they can control the generated styles again, like the style GAN v2, this is the adaptive instance normalization. I should say, style GAN v1 was published before style GAN v2. Let's take a look over this one. So it means, so this is style GAN v1, this is style GAN v1, style GAN v2. So which we can assume style GAN v2 learn something from style GAN v1. And this is the innovation in style GAN v1. It creates the mapping networks and use the distribution in the W space to control the control the style. So that's why they call it the style GAN. So we show they propose select AHQ for progress GAN. And for style GAN v1, they propose another dataset named FFHQ, flicker phase high quality. So the resolution is the same, but there are more images. And the difference between select AHQ and FFHQ is because all images in the select AHQ are from celebrities. So they want to create another dataset. There are more variety. For example, you will not see a baby's face in the select AHQ dataset. And there is also no very, very old man and a very fat man and some people with customs and makeup on their faces. So this is a more various data. Okay, so let's go back to this mapping network. Why do they need the mapping network? Because they explain it in their paper. So in real dataset, we seldomly see long hair male images. Okay, this means what? If we assume the distribution in the latent space is Gaussian, it may not match the real distribution in the real world. So their mapping network can convert a Gaussian distribution to some other distribution that is more similar to the real world data image distribution. Okay. So their baseline is progressive GAN, and they add some mapping styles and remove the traditional input. Traditional input just means the random variable, the latent space. And they use the new mapping function to create a new input, the W space. And then they add the noise and mix some regulation. So this is the FID value for the two datasets. It shows with the new design, they create a better image qualities. Okay. And why do they need to add noise? They explain the reason here. So this is the case for all layers. They add noise. But this is the result for all layers. There is no noise. Okay. So without noise, the style GAN easily generates blurred hairs. Okay, so these are the two cases. Because style GAN is a very deep network. Let's take a look here. Okay, maybe I forgot to show it. Okay, but however you will. Its baseline is progressive GAN. So progressive GAN is from 4x4, 8x8, 6x16. Style GAN v1 has the same structure. The only difference is how they create the input latent vector. Okay, so here, for if they only add noise to the high resolution layers or low resolution layers, they will generate a result like this. So this like the oil painting hairs. But so they found for style GAN V1, the best settings add noise to every layer. So let's see some result. This is the source A and source B. Source A, unlike a style GAN, a star GAN V2, you see a very similar result in star GAN V2. Let's take a look. Star GAN V2. Okay, so this is star GAN V2. There is a source image and a reference image. They can mix. I should say they can take the style from the reference image and add it to the source image. Okay. And let's take a look of the style GAN. It has something similar. Okay, but however, there is no reference and the source. Both of the row of the images and the column of the images are generated by different latent variables. Okay. They are all fake images. Okay. Then, okay, let's see. Let's recall progressive GAN from low resolution and slightly larger. So it calls the coarse layers and the fine layers. So if they use the latent for the style for this image and replace certain layers, use latent from these images, they can generate the mixed style. So okay, let's take a look. For this color, you can see they all share the same skin color. And for this row, for the 3 rows, you can see the coarse style control what? Control the should say the skin color. And for the 5 high resolution layer or the 5 styles, these rows all share the same what? Okay, it's hard to say. What do they share? Color of skin, color of hair, maybe. Okay. So style GAN, it means they can control styles at different layers. And the comparison of star GAN V2 and the style GAN V1 star GAN V2 is a style transfer GAN. You must have a reference image and input image. It transfers the style from the reference image to the input image. But the style GAN is not a transfer GAN. It generates images from random variables. Okay. So there's no head-to-head comparison. And from their GitHub website, you can see if you just want to use Tesla V100, okay, the GPU we have in our AI center. Then, if you just use one GPU, you need 41 days to train the network. It is very, very long. And if you use 8 GPUs to train this resolution, you still need 6 days. Very, very long. So the Keras, the author, he is a researcher at NVIDIA. NVIDIA has a lot of computational resources. So let's see some results. So this is the LSAN dataset for bedroom, and this is the LSAN dataset for the car. And this is the LSAN dataset for cat. Okay. For celeb AHQ dataset, because all of the faces are well aligned, so we can easily observe, oh, there are some relationship. The different layers control different style. But for the 3 dataset, cat, bedroom, and car, because they are not well aligned, so if we only observe the 3 dataset, we have no idea what styles do they control. Because of the cell GAN is very, very successful, and there is a website that you can find. This person does not exist.com. It can generate face images, and just like a style GAN V1, they are generated from latent random variable. So the person never existed. And it charges users. If you want to buy a 124 square images, you can pay $15 US. Okay, interesting. And they can choose gender, age, and ethnicity. And I try to choose the same setting as mine. I would like to, can it generate an image very like me? But well, I cannot do it. And then there is an interesting video released by Keras, the first author. And okay, how to play it? Let's see. Doesn't work. Okay. That's the reason they need to add the noise to the, when they can change the noise strength. So when there is no noise, the hairs are blurred. And okay. They can also the style scale 5. So let's stop here, and because we have other GANs and the diffusion model to need to introduce. Right. Okay, so 1 year later, they published the style GAN V2. So V1 is very impressive, but what's the problem? They found 2 drawbacks. First is the drop light artifact. It means for some small regions, the generated image, the region are blurred, very blurred, and the shape like a drawlet. And the second is the face artifact. Face artifact means for the 3 faces, the 2 teeth are aligned at the same location. That is not correct, because when the face is not upright frontal, the location should slightly shift. So they propose. Okay, let's see the. Okay, there is go. Okay. Some failure cases. For example, this is a drop light artifact. Here you see the hair is not a straight line. There are some curves. And this is another one. There are 3 droplets and the generated results look like totally failed. So they checked the research, and they found that if they use progressive growing, they cannot avoid the problem. Okay, they found the GAN, the generator, when it grows from low resolution to high resolution and further high resolution, well, they need to learn some high frequency detail at some fixed location, like this one. The T's are the high frequency detail, so that the generator will remember the location, and so that it will generate the droplet, the very high, gradients there. So this is their new methods. Use the new method, they won't have the problem, and this is architecture of their method. Okay, so this is the cell GAN V1, and the A and B are the same image, just in B there are more details. So they revise the architectures and add a weight demodulation into it. Okay. Then, like a cell GAN V1, with the new designs, their FID value decreased, and path length also decreased. I will explain path length later. Okay. So for the FHIQ, there are some combinations. They show the new one will be the better. So what is path length? Okay, let me explain. So what's the beginning of the latent? This is a latent or random variable in the latent space, right? So because we know convolutional network is not linear, so if we just sample two random variable or latent variant in the latent space, their generated results may change a lot, differ a lot. Okay, so they want to measure if we have a small shift in the latent space, how much will be the difference in the output domain, just in the space. So this is a definition of latent path length. Okay, if the shift in the latent space very, very small, say just 10 to the negative order of -4, then how to do it? Okay, they measure the perception. They generate two different images, right? And they use VGG, pre-trained on ImageNet, to extract, or say, to convert the feature space from the image to the two images. And they can compute the difference between the two images, two vectors. So this will become, and if they randomly sample a lot of pairs of latent codes, they can calculate the average means of the difference on the image feature space. So that is the path length. Therefore, if the value is small, it means the generator is stable. Small distribution, small dispersion in the latent space will not generate a lot of difference in the image space. And there's another matrix called precision and recall. Okay, so the matrix, we say FID is a matrix to measure the image qualities generated by GAN. For most cases, it works, but for some cases, it doesn't work. So for what kind of cases it doesn't work? And the precision and the recall matrix was proposed to address this problem. So let's take an example. This group of mixed images, their FID value is 32. And this group of images, their FID value is 29. Usually we will say the lower FID value, the better image qualities. But which one? do you think the quality is better? This one. Okay. And for these images, face images, the validity value is 65. And for this set of face images, the validity value is 62. The same. We usually say the lower FID values, the better quality. But in this case, this group of images is better than this one. Okay. So the precision and the recall matrix want to address this problem. They propose the precision and the recall calculation. Okay, and so that style GAN V2 use the matrix to show their performance of style GAN V2 on the precision and the recall. But however, you can see here, style GAN V1 precision is better than style GAN V2. Okay, and here again, style GAN V1 is better than style GAN V2. So, because there are several different metrics, just like a PSNR and SSIN, either of them has their own pros and cons. So, for style GAN V2, they just show off that, okay, and let the readers and the reviewers judge those numbers by themselves. Okay, okay, there are some very interesting numbers. You can find a table from style GAN V2 GitHub website. It means to do research for style GAN V2, this is the overall GPU years, not days, years, measured by a single Tesla V100. So, in the beginning, they found there are some artifacts. So they need to reproduce those artifacts as much as possible. So they try a lot of images, and okay, then they want to write a paper to show their result. And finally, they need to create some videos to demo the advantage of style GAN V2. So overall, they use 51 years GPU time to finish the project. Okay, so it's again, this is a team from NVIDIA. They have a lot of GPUs to run it. Okay, so the code and the pre-trained model are available at GitHub. And they also show if you only have one Tesla V100 and you have say only 10K images and the resolution is low, you still need 13 days to train the model. It means, well, I should say, it's very difficult for me to reproduce their result using our school's AI center's resources. Okay. So let's see some results for the code. Oh, this website is not publicly available. You need to go to their GitHub website and their link. Then you can click a link and go to this private, I should say, not public YouTube video. And there is no sound. So they will show the artifacts looks like this one. Here, this is the drop-like artifact, and follow the red circle. Okay. When they track and when they see the feature maps, they see they found the reason, and they developed a new architecture to solve the problem. Okay, so let's stop here. If you are interested, you can take a look by yourself. All right. Then 1 year later, style GAN V3 was published. So today, now what's the problem? We have V2 and we still have V3. Okay, they found a new, I should not say problem. Okay, so from the title, let's see, you can see what the problem they want to solve. Alias-free generative adversary network. So they found style GAN V2 generated some alias artifacts. So what is alias artifacts? Let's take a look. Okay, this is the alias artifact. This is the cat, right? So it means the cat is generated by a latent variable in the latent space. So if they not only sample one latent variable, but also sample some other nearby latent variables, it means they should generate images slightly different. Okay? And then when they average those generated images, theoretically they should generate a blurred image like this one. But blurred image like this one. But in fact, the style GAN V2 doesn't. It generates some patterns on these images. Okay? And this is another example. This is the image generated by the first latent code. And this image is generated by another latent code. They can do interpolation, right? When they do interpolation, what they expect is they will see the smooth change of the hairs. But in fact, they generate some patterns for style GAN V2. It's not difficult. Okay, so let's take a video. It's easier to understand. A video, yeah, like this one. Okay, so this is expected result, but this is generated results. Okay, and how to solve the problem? They use a new architecture, a very complicated architecture as this one. Okay, and okay, what's their modification? Based on style GAN V2, they generated a Fourier feature, the frequency feature, and there's no more noise input. They take it away, so that they can. Why it is important? Because if they want to generate the continuous hairs, okay, you see, when in style GAN V1, add noise. They add noise because they want to see the detail of the hairs. But now they found, okay, those noise or the architecture will generate those alias patterns. They don't want it, so they took the noise away, and they add a lot of more regulations, and so they generated the best FID value. Okay, and the EQT and the EQR are two metrics. Okay, it is equivalence matrix for translation and for rotation. Well, the two matrices are developed by the NVIDIA team themselves, and the two matrices are borrowed from another paper like this one. Okay, so they show some quantitative comparison. So compare with style GAN V2 for the FFHQU. So FFHQ is the flicker phase high quality dataset, and the U means unaligned. Okay, so it can be anywhere. Then we will see some images later. And the FFHQ, So the meta face is the Metropolitan Museum of Art Collections. All of them are paintings. Okay. U means also unaligned. The AFHQ2. AFHQ is the animal face, high quality, and this is a new version. And the beaches are a lot of beaches. No, there's no human faces there. Okay, and they show some training convergence. So their style GAN V3 will generate a better FIDs compared with style GAN V2. So there are two versions, style GAN V3 for rotation and style GAN V3 for translation. Usually this is the best one, and this also the one they proposed. So let's see the result. So this is the style GAN V2, and this is style GAN V3-T. Is style GAN V3-R. This is the best proposed. But however, for 2D images, it's very difficult to see the difference. Even if I show more images for you, it's hard to see. Okay, because they also can show some style mixing. But however, if I show a video for you, it will be easier to understand. So let's take a look. So like this one. Do you see some fixed pattern here? But for the style GAN V3, there is no the aliasing pattern. Can you see from the image? Do you see the location of those breaths are the same, but it will move in style GAN V3. So, okay, now how do they generate those images the same? Just sample a latent vector and another vector, do linearization, do interpolation in the latent space, and they can generate many images through their generator. Another example image. So this is a metaface dataset. There are some patterns, aliasing on the hair, okay, even on the face. Okay, so this is the improvement of style GAN V3. In AFHQ dataset, okay, can you see some? Oh, okay. Well, for you who have a laptop, maybe it's better to watch the videos using your laptop because the contrast here is not very good. All right. Okay. So now we see a lot of GANs generated faces, but they are all other different GANs. This is the enlightening GAN. Okay, it is introduced by your classmate, and the purpose of this GAN is to improve the brightness of a very dark image. Okay, and all right. Okay, now we finish the introduction to GAN, and let's go back to our diffusion model. So you see the interface last week, okay? So here, the model is the diffusion model you can choose. And there is the clip, skip, and the VAE. All of them are computer vision models. And because we don't have enough time, so diffusion model, there are three important papers for the model. The first one was published in 2015. It was the concept of diffusion model. What is diffusion model? It means if there is an original image with many steps of adding Gaussian noise, then it will become finally a noisy image. So this is called diffusion or forward processing. So if we can learn something called a reverse trajectory, then from a noise image, we can step by step and converge it back to an image. So this is diffusion. But the problem is how to learn the model. Okay. And they show in the 2015 paper, they show an application for implanted. So it means given an image and they crop the region and they want to refill this region. This is called the implanting task. So they can train a lot of bug images, like this one. All of them are bug images. And add a lot of noise and many steps they can generate step by step and all of them. And then learn a simple reverse trajectory and apply it on this. In the beginning, this is a region we want to implant. And add a Gaussian noise, then step by step and restore the image. So this is a restored result compared with the ground truth one. The refilled region looks different, but it looks like a bug image. So this is another example. They train, this is the emit data set. They train a diffusion model, the trajectory, so they can create those images from noise, from random numbers. Okay. So for stable diffusion models, there are a few issues. First is, what is the diffusion rate? Diffusion rate means from this step to the next step to the next step. This is the Gaussian noise. But how much noise would you like to add? Okay. And then, how do you handle? Because image intensities are all positive. But if you add the Gaussian noise, sometimes it will become negative. How to handle this? And how do you model the reverse trajectory? It means if you only have the t plus 1 to t, xt plus 1 to xt, those noise value, how do you predict the clear value, the step by step? Okay, then 3 years ago, or 2 years ago, okay, there's an important paper called DDPN. It proposed a very simple, straightforward method to model the diffusion model. Okay, so it means given when you train the image, you learn the alpha parameter, and when you do the okay, then you just use you learn the alpha to reconstruct it. Okay, the mathematical, but the equation here looks very simple, but the mathematical derivation is very long. If you download it, GitHub papers, you can see. Okay, and sorry, let's see their result. This is the result generated by their method. It's only select AHQ 250 square. Okay. But compare the state of the art. Okay. There's no number report for the select AHQ. And for style in 2 years ago, progressive GAN, style GAN 1 to V1 and V2, all of them worked for very large. But they didn't. They only show result of 250 square. And if you see the FID values, theirs are not the best one. So this paper is important, but it doesn't attract a lot of attention until stable diffusion was released. So the easy diffusion you used, in fact, the algorithm behind is stable diffusion. So what's the contribution for tourism? It means to the DDPN, it do step diffusion model on image itself. But the stable diffusion doesn't. It do diffusion models on the latent space. So this is a latent space. Because it do diffusion model on the latent space, we can add a lot of conditions. So that's the reason when you type those texts, they are conditions. So you can generate images like this. Okay, given some text prompts, and you generate the images. Okay. And also like this one, this you can find those papers. So okay, the next problem, the next question is, how do your algorithm know the given text prompt should be used to generate what kind of images? So 2 years ago, there is a paper called CLIP, Contractive Learning Image. It means it is proposed by OpenAI. Now you all know OpenAI is a company of ChatGPT. They train a very, very huge data set. How huge is it? Okay, there are 400 million image and text pair. Okay, and they train 18 days to do it, and they use 592 V100, the Tesla 100 image to train the paired text and image data set. So when they train it, given any text, they can know, I know what image it should be. That's the reason we can use diffusion model to generate the image we like. And that is also the reason when you see the user interface, you will see it's more clip, skip. The clip is left clip, just like left clip. So, okay, so that's the. So if you want to know what the clip means, you can take a look of this paper, right? And okay, because there is one image encoder and the text recorder, so there are many combinations, and then they find that the best combination is what we got. Okay. Right. Okay. So now you run out of time, and next week you need to share your findings to generate the images, right? Okay, this is your homework 4. Okay, and I suggest you try to make a very, very funny, because you can create any kind of images. Try maybe let me show your innovation. All right. Okay. All right. That's all.